professionals. Okay, whereas in case of OLAP, it is used by the data analysts. It is used by data analysts such as knowledge workers, okay, managers, high-end people. So who, I mean, for performing this OLAP operations, I mean, for accessing this OLAP system, knowledge required is more compared to OLTP users. OLAP users require more knowledge compared to OLTP users. And coming to the contents present in these two systems, OLTP always maintain the current data, which is too detailed, and OLAP maintains historical data. It manages the historical data, and in addition to this detailed data, we have the detailed data, but in addition to that, OLAP will provide summarized form of the data at different levels of granularity. Okay. Collecting the summarized data will help in decision making. And database design. Yeah, OLTP system will use entity relationship database design. OLAP system have a different, different database design models, such as star schema model and Snowflake and fact constellation. We have different models. We'll discuss in today's class. Yeah, coming to view. So OLTP system, it focuses on the current data within the enterprise or department without referring to the historical data present in other organizations. Whereas OLAP system, it will deal with the information which generates from other organizations also, from different organizations. So that is integrating the data from many stores. And access patterns. In OLTP, we have shortened atomic transactions. So it performs both read and write. Whereas in case of OLAP, it mostly performs read-only operations, because frequent insertion, frequent deletion, these kind of operations will not be done on the historical data. Okay, only from time to time, at regular intervals of time, new data will be updated in the OLAP system. They will perform updates, not frequently. Okay, so data will be updated but not deleted or modified. Yeah, so this is our topic, data warehouse models. So we know this entity relationship database model, right? So that is for OLTP systems. And coming to data warehouse models, yeah, here models can be of three types. Data warehouse models can be of three types. One is enterprise warehouse. Second one is a data mart. Third one is virtual warehouse. So we'll discuss about these. First one is enterprise warehouse. So this model will collect all the information about multiple subjects present in the organization. Okay. So if multiple departments are involved in the warehouse, in the organization, then data is collected from all these departments, from all the functional areas of the organization. So it maintains detailed data as well as summarized data. And the data will range from gigabytes to hundreds of gigabytes, terabytes, or beyond it. Means large data will be maintained in enterprise warehouse. And for implementing this enterprise warehouse, high-end systems are required. Traditional mainframe systems, super servers, parallel architecture platforms, because it's handling large data. So it's not implemented on personal computers. It requires high-end computers. Okay, so it requires extensive business modeling, and the time that takes for building these types of model, enterprise warehouse model, is very large. It may take years to design and build this enterprise warehouse model. And next category in a data warehouse model is data mart. So this is, you can call this as a subset of the warehouse. Subset of the warehouse. It maintains the data based on the department. So it is customized to the department. Data marts are maintained for the departments. It spans only the single department, not the complete functional areas of the organization. It's maintained for a specific functional area of the organization. And these are small in size and are usually implemented on low cost departmental servers. High configuration is not required, as we need an enterprise warehouse. High-end configuration is not required for data mart. Okay. And the implementation time for building this data mart is less compared to warehouse. So it can be measured in weeks rather than months or years. Implementation cycle of data mart is less. And depending on the source of the data, this data mart can be categorized as dependent or independent. So we have two types of data marts: independent, dependent. I mean, from where you're collecting the data, based on that data source, data mart can be either dependent or independent. If you are collecting the data from the enterprise data warehouse, if you're collecting the data, then we say it as dependent data mart. If you collect the data from the regular operational system or the data that is generated locally within a particular department, then we say it as independent data mart. Simply, if data mart is created from the operational database, we call it as independent. If data mart is created from already created warehouse, if you're creating a sub part of it, then it is dependent data mart. Okay. The third category is virtual warehouse. So this is actually a set of views over the existing operational databases. This is used for efficient query processing. Okay. So, and it is easy to build but requires excess capacity on the operational database servers. Means actual warehouse is not constructed here. As we learned the views concept in our DBMS, similarly here, virtual warehouse is a collection of views from the operational databases. So these are the three categories of data warehouse models. And coming to the difference between data warehouse and data mart, so mostly we'll be confused between what is data warehouse and data mart. So for that, I have listed few attributes and how these two differ. Coming to scope of the data, data warehouse will maintain enterprise-wide data, whereas data mart will maintain department-wide data. For example, you consider our organization, SRM University. So we have multiple departments. So if you maintain department-wise data, then we call it as a data mart. If the data is maintained based on all the departments, then we name it as a warehouse. Okay, that's the meaning of enterprise-wide and department-wide data. And number of subject areas involved. In case of data mart, only it's related to one subject area, whereas data warehouse maintains multiple subject areas data. And how difficult to build. So data warehouse is difficult to build compared to the data mart. And the time taken for building this enterprise data warehouse is more compared to data mart. And amount of memory is also large for data warehouse compared to data mart. Okay, time taken is more, the amount of memory required is more, and the complexity is also high in case of data warehouse compared to mart. Yeah. Data cube. So we learn about this data cube because it's a modeling technique. We can view the data in multiple dimensions. So this data cube, it allows the data to be modeled and viewed in multiple dimensions. And every data cube will be defined using dimensions and facts. Every data cube will be having dimensions and facts. So the data cube is a data model which is used for representing the data in a data warehouse. Okay, so we have learned this enterprise warehouse model, this data marts and virtual warehouse. Okay, So they are all the different models. I mean, practically, how will you implement those models using this data cube? So data cube will be defined by dimensions and facts. So this is a multi-dimensional data model. Data cube is a multi-dimensional data model. In case of what's that? In case of our DBMS, we know only two-dimensional data, right? Rows and columns. But here, multiple dimensions can be viewed with the help of data cube. Okay. So coming to these dimensions, so what do you mean by a dimension? It is an entity with respect to which an organization will maintain the records. Organization will maintain the records based on the dimensions. For example, if you consider this all electronics company, we have a sales data warehouse. So it will maintain the records based on time, based on items, based on the branch, based on the location. So these four dimensions are used. Okay, so these are few dimensions which I mentioned here. These are used for creating the sales data warehouse. Okay. So every dimension is associated with a table and we call it as the dimension table. So we have time, a dimension table, item table, branch table, location table. So every dimension will be having a table. For example, if you consider item dimension table, so it will contain the attributes such as item name, brand, its type, so on. So that is a dimension. So it is an entity with respect to which an organization will maintain the records. That is the dimension. So, and the next one is facts. So data cube is defined by using dimensions and facts. So facts are the numerical measures, means the quantities by which we want to analyze the relationship between the dimensions. How you would analyze the relationship between multiple dimensions? So we need a numerical measure that is called a fact. In case of sales data warehouse, facts will be like dollars sold. So this is the sales amount in dollars, units sold, number of units sold for each item, and amount budgeted. So all these are numerical measures, quantities. So these are said to be the facts. And we maintain a fact table. So fact table contains names of the facts as well as a key to each of the related dimension table. We already mentioned that these facts are used to analyze the relationship between multiple dimensions. So what are all the dimensions involved in this fact? So each one will be having a key. Fact table contains numerical measures as well as a key to each of the related dimension tables. Okay. So we'll discuss with examples. You can see here. So this is a two-dimensional view of the sales data in all electronics according to two dimensions. So only two dimensions are involved here. One is time and item. So according to time and item, so this is a 2D sales data for a location Vancouver. For a location Vancouver, so we are maintaining the sales data. So time and item are the two dimensions used. So time dimension, I mean here we are using quarter 1, quarter 2, 3, 4. Past 3 months quarter 1, next 3 months quarter 2, so on. The item type also, there are 4 item types: home entertainment, computer, phone, security. So all these numbers indicates sales data, sales in dollars, $1,000. Yeah. So this is a 2D representation. And coming to 3D representation of sales data. So the third dimension that is considered here is location. So third dimension is location. So you can see here for location Chicago, New York, Toronto, Vancouver, and at all the time quarters for all the item categories, you are representing the sales data. So this is a 3D view of the sales data. So this can even be represented using a data cube, 3D data cube. You can see this is a 3D data cube. So one dimension is item, another dimension time, and another dimension is location. So item dimension is maintaining the information based on the item type, and time dimension is maintaining information based on quarters, and location dimension is maintaining the information based on the cities. So 4 cities, 4 quarters, and 4 item types. And each value in the cell represents the sales information. So a cube in this cell will represent, for example, this 400. So this 400 will represent sales in Vancouver city. Sales in Vancouver city for security related items in quarter one sales. So these sales are being increased. You can see here 512. So in the next quarter, the sales were increased. In the next quarter, the sales were decreased. And again in quarter 4, the sales were increased. Okay. And this is 4D data cube representation of the sales data. And the 4th dimension that is considered here is supplier. So this is one data cube which represents the sales of the items supplied by supplier 1. This second data cube is sales of items supplied by supplier 2, and this is supplier 3. Okay. So for each supplier also we are maintaining the information. So this collection of 3D cube is 4D data cube. Okay. So this represents a collection of 3D data cube. Similarly, any n-dimensional data can be represented as a series of n-1 dimensional cubes. You can see here. So this is the 3D data. 3D data can be represented using this 2-dimensional data, right? Collection of 2D data. This is one. Wait a second. So this is one 2D table. This is another 2D table. This is another. This is another, right? So 3D data can be represented as a series of 2D data. Okay. Similarly, come to the next slide. Yeah, this is also 3D data, and this is 4D data. So this 4D data cube is a series of 3D cubes. This is one 3-dimensional data cube. This is one more 3-dimensional data cube, and this is one more 3-dimensional data cube. So a series of 3D cubes can represent the 4D data cube. Okay. Similarly, any n-dimensional data can be represented as a series of n-1 dimensional cubes. So this data cube is a metaphor for multi-dimensional data storage. Okay. Means it will describe the multi-dimensional data storage. The description of multi-dimensional data storage can be represented in the form of a data cube. But actually, the physical storage is different from the logical storage, right? The actual physical storage of the data will differ from the logical representation. In a simple way, I hope you learned about arrays. What is a one-dimensional array? For example, series of numbers 10, 20, 30, 40, 50. So this is a one-dimensional array. You might have learned in your C language or Python anywhere. And if you consider 2D array, what is 2D array? 2D array is a collection of 1D arrays, right? For example, 2-dimensional array. I am considering the collection of 1D arrays. So this is 1D array, this is 1D array, this is 1D array. Collection of multiple 1D arrays, we call it as a 2D array. Similarly, collection of these kind of 2D arrays, we call it as a 3-dimensional array, right? So how will you represent it logically? In this way, we'll represent. Logically, we'll represent. But how they will be stored in the memory? Yeah, we know. In case of main memory, we treat main memory as a series of cells, each cell having certain memory location, right? So in this way, a 2D data. Okay. So if this is the location is 1000 and if it is integer spanning 2 bytes of memory, then the location of this will be 1002 and location of 30 will be 1004 and this is 1006 and 50 will be 1008 and this 5 will be 1010 like that, right? So this is the actual physical storage. Physical storage representation is different from the logical representation. Logically, we'll represent in this manner, but physically, all the values will be in sequential memory location, right? So data cubes are n-dimensional and they are not confined to only 3D. So we may think that data cube means only 3 dimensions. No, it's not the case. So data cubes are n-dimensional and it can be more than 3-dimensional also. In data warehouse literature, we call this data cube as cuboid. We also call it as cuboid. Okay. So given some set of dimensions, we can generate a cuboid for each of the possible subsets of the given dimensions. Okay. And the result will be a lattice of cuboids. Yeah, I'll show you the example. Yes, this one. See, so this is a lattice of cuboids. We can also call it as 4D data cube, as we maintain data in 4 dimensions. One is time, second one is item, third one is location, fourth one is supplier. So it is a 4D data cube for the dimensions time, item, location, and supplier. Okay. So here we can see every cuboid will represent a different data at different degree of summarization. Means you can see this cuboid which holds the highest level of summarization. Highest level of summarization means, so this is called the zero dimensional cuboid, which or apex cuboid. It's also called as an apex cuboid. So it represents the sales of all items at all the locations supplied by all the suppliers at all times. It's a single value. It's the highest level of summarization, a single value which represents the total sales, combining all the dimensions. And next level, 1D cuboids. 1D cuboids represent data related to each dimension. For example, time. So this data cuboid contains for every quarter, time means for every quarter. For quarter 1, what are the sales data at each item, at each location, at each supplier? Okay, so this is for time. This cuboid maintains time related information for all the items at all the locations supplied by all the suppliers. Quarter 1 sales, quarter 2 sales, quarter 3 sales, quarter 4 sales. Similarly, item. So this 1D cuboid represents the data based on for each item. For each item, what is this? What is the sales at all the times, at all the locations, at all the suppliers? Okay. And coming to the next level, 2D cuboids. So here, what are the dimensions considered? Time and item. So for time, quarter 1 and item type home entertainment, what are the sales? And for time, quarter 1 and another item, what is another item? Security, what are the sales? And time, quarter 1 and what? Phone, what are the sales? And time, quarter 1 and entertainment, what are the sales? Similarly, for a time, quarter 2, what are the sales of this? Home entertainment, security, phone, entertainment category item. So based on the time and item, we can maintain the cuboid. That is 2D cuboid. Here, so how many possible combinations will you get? If you have 4, how many combinations you will be getting? 6. That is 4C2. 4C2. So time item, time and location, time and supplier, item and location, item and supplier, location and supplier. And coming to 3D cuboids, it will maintain the data based on 3 dimensions. So if you have this 6 possible 2D cuboids, the next level you'll be getting 4. 4C3. 4C3 is 4. So this is 4C1, which is 4. This is 6, like that. So based on the 3 dimensions, it maintains the data at each time value for each item, for each location. So this is time, item, supplier, time, location, supplier, item, location, supplier. And coming to this last one, which is called the base cuboid, this provides lowest level of summarization, which is called detailed data. It will be having detailed data for each time, for each item, at each location, supplied by each supplier. 4D data. It's a detailed data. Moving up on the cube, the data will be summarized. And at the apex cuboid, data reaches highest level of summarization. So all sales, total sales of all the items at all the times, at all the locations, supplied by all the suppliers. So this base cuboid is detailed data for every time. We have time, how many values of time are there? Q1, Q2, Q3, Q4. Items, 4 category: home entertainment, security, phone, entertainment category. Locations, we have 4. Vancouver, what are they? 4 we have. Vancouver, New York, other 2, I don't remember that. So we have 4. And suppliers. For example, if you have 3 suppliers, supplier 1, supplier 2, supplier 3. So this is the detailed data. Okay. So this is lattice of cuboids, which represents cuboid at each level. At each level, we can see multiple cuboids. So this is the logical representation. This is the logical representation of lattice of cuboids. Okay. So data warehouse will maintain the data at different levels of summarization, from lowest level of summarization to highest level of summarization. Yes. So after discussing these schemas, I'll conduct a quiz. Okay. So yeah. So a multidimensional model will exist in the form of star schema, snowflake schema, factor constellation schema. So these are the 3 schemas that can be used for modeling the data warehouse. Okay. First one is star schema. This star schema will maintain a data warehouse. So this, in case of this star schema, we'll design a data warehouse with one fact table. What is fact table? We have learned just now. Fact table will maintain the numerical measures. It contains the numerical measures along with the key to each of the related dimension. That is fact table. Okay. And also multiple dimension tables. The data warehouse will contain single fact table, multiple dimension tables. One table for each dimension. One table for each dimension. Okay. Yeah. So why we call this as star schema means there will be a single fact table surrounded by multiple dimension table, which contains this fact table, right? It contains keys to all the related dimension tables, which which looks like which represents its starburst. Okay, this schema graph will represent starburst with the dimension tables displayed in the radial pattern around the central fact table. This is central fact table. These are dimension tables. Yeah, we can see here. So what are the dimension tables? Time dimension, item dimension, location, and branch. So what is a dimension? So these are the entities based on which the organization is maintaining the data. We have 4 here. So coming to this time dimension, we maintain the data with respect to the attributes, day, day of the week, month, quarter, year. So day represents, it can be from 1 to 31. Day of the week means Sunday to Monday. Next month, 1 to 12. Quarter, 1 to 4. Year, so based on the yearly data that they are using. Maybe for example, 2005 to 2020, like that, yearly data. This is the time dimension and this is the key. So every record will be maintained using a uniquely identified using a key. So this is the time key. Similarly, item dimension will be having its key, name of the item, its brand, type, supplier type. Who is supplying that item? Supplier type. And next, location. So location key with street, city, state, country. And next, branch table. Branch key, name of the branch, type of the branch. So these are few dimensions along with their attributes mentioned here. And next, this is a sales fact table. We know fact table will contains key to each of the related dimension. So here sales fact table is related to all the 4 dimensions. So it maintains key to time, key to item, key to branch, key to location, followed by the numerical measures. So what are the numerical measures here? Dollars sold and units sold. Sales information. So we made, this is a sales warehouse, right? Sales data warehouse. So sales information related to dollars sold and number of units sold. So this is STAR's schema for all electronics company. Using this, that's the first schema, that is STAR schema. Okay. So we have 3 types of schemas: STAR, a snowflake, and the fact constellation. The next one is snowflake schema. So this is an extension. You can call it as an extension or a variation of STAR schema model. The only difference is here the dimension tables maintained in the STAR schema will be normalized and split into additional tables. We'll split the dimension tables into additional tables. We are performing the normalization. Why we do the normalization? To reduce redundancy. To reduce redundancy, the dimension tables can be further split into additional tables. Okay. Yeah, here the advantages and disadvantages are mentioned. So the major difference between these two is dimension tables of the snowflake model can be normalized in order to reduce the redundancies. So what is the advantage of using this snowflake schema is, yes, it will reduce the redundancy, and as the tables are split into multiple, they are easy to maintain and saves the storage space as it reduces the redundancy. Okay, it's easy to maintain. And next disadvantage is, yeah, that is the problem with the normalization. We need to execute more join operations. For executing a query, we need to perform more join operations. It may reduce the system performance because join operations consume more time for execution. Okay. So normalizing the dimension tables into multiple additional tables results in the snowflake schema. We'll see this example. Yeah, this one. Same as STAR schema. So we are having time dimension, branch, item, location. See, Here, the item dimension table is split into item and supplier. This item dimension is normalized and location dimension is normalized to city dimension table. And everything is same. Only these two tables, we found that redundant data is there, and then we can, because we are maintaining the item, based on each item, we are maintaining the information. So there are, for example, if you consider 3 suppliers, and if there are some 1,000 items, so in reality, there may be more than 1,000 items also and more number of suppliers also. For example, I'm considering 3 suppliers with 1,000 items, and these 1,000 items, for example, 800 may be supplied by supplier 1, and 100 may be supplied by supplier 2, and 100 may be supplied by supplier 3. So all these will be repeated for 800 times, and this will be repeated for 100 times, and this will be repeated for 100 times. So redundant information. In order to read, 1 minute. Here. Here we are in this star schema, we are maintaining the supplier type in the item dimension table. If that is the case, data will be redundant. More number of, S1 will be repeated for 800 times, S2, S3. So in order to reduce that, this item dimension is split into supplier table. So now we'll have only the key information. We'll maintain the key information, and the supplier information is maintained in a separate dimension table. Similarly, in case of location table, if you consider a city information, okay, so this will be repeated mostly. This state, country, and city information will be repeated mostly. And the street information will be less redundant comparatively. Comparing this street with city, state, and country, street will be repeated less number of times, whereas city, state, and country will be repeated more number of times. Okay, so this city table can be separated and maintained as an additional table in order to reduce the redundancy. So location table is normalized to city table. Okay, so so this forms the snowflake schema, and we have a key to this and a key to this. We have to maintain the key. City key is maintained in this location table for this city, and supplier key is maintained in this item table for this supplier table. The next one is fact constellation. So fact constellation schema means instead of single fact table, if you maintain multiple fact tables, instead of single fact table, multiple fact tables are maintained. Then we call that schema as fact constellation schema. Okay. For example, if you consider enterprise data warehouse and data mart, we know data mart maintains department-wide data. Enterprise warehouse maintains total organization data. Okay. So this data mart, for this data mart, star schema is suitable. Single fact table will maintain the data related to that particular functional area. Whereas in case of enterprise data warehouse, single fact table is not sufficient. We need multiple fact tables. So in that case, we go for fact constellation scheme. For enterprise data warehouse, for modeling this enterprise data warehouse, we go for the schema fact constellation. We can see here, in addition to sales fact table, we are maintaining the shipping information also, shipping fact table. So this shipping fact table contains some related dimensions. So it's related to time, related to item, shipper information. So a separate dimension table is maintained for shipper, and location, from location to location. From From this location to this location, the items are shipped, and the dollars cost and the number of units shipped. So this is one more fact table which is maintained. So whatever the dimensions are related to this fact table, it is maintaining the key to that dimension tables only. So multiple fact tables are required in some sophisticated applications. In that case, we go for fact constellation schema. It's also called as the galaxy schema because multiple stars are involved here. That's the reason why they call it as galaxy schema. And the next one is OLAP operation. Okay, before discussing this topic, yeah, I'll give you a quiz. Try to answer that. Do you have any queries, students? Okay, let me share this quiz. Now the time is 2:03. By 2:09, you have to complete. Last 1 minute. Try to complete. We'll release the scores. You can check it. Yeah, you can check your scores. Okay, we'll discuss these answers and then I'll move on to the next topic. Yes, first one is dependent data marts are sourced from operational systems. No, so this is false. Actually, dependent data marts are sourced from warehouse. So the given statement is false. So if the data marts are sourced from operational systems, we call it as independent data marts. This is false. And next, department-wide data is efficiently handled by data mart. The answer is data mart. Enterprise-wise data, it's handled by the enterprise warehouse. Whereas department-wide data, we can go for data mart. And next, match the following. Yeah, here we can see data cube, which is a multidimensional model, and base cuboid, which is more detailed, apex cuboid, which is 0D cuboid. So the answer is 1C, 2B, 3A. Yeah. Last one, 1C, 2B, 3A. And next one. Facts, these are the measures. Dimension table, it will describe the attributes. Data cube is also referred as the cuboid. So 1B, 2A, 3C. So second one is the answer. Next, last one. Yeah, star schema. So star schema contains a single fact table. Next, snowflake schema. It performs normalization, so normalized tables. Fact constellation schema, multiple fact tables. So the answer is 1A, 2B, 3C, this one. Any doubts, students? Okay, let me continue with the next. Yeah, 1 second. I'll explain you about this course project. In the last class, I forgot to explain you. you have any queries regarding this, you can ask. I'll wait for a while. Can you see the screen?
Yes, ma'am.
Okay. Yes. So in this project, you need to apply the data mining algorithms and techniques to solve some real world problems. You can choose any problem and you can solve it using data mining tasks. So any related problem can be selected. And for your understanding purpose, I've given some 6 examples. So these are just sample example problems. It's not that you have to choose only from these 6. No, it's not that. Okay, you can select any real world problem. Okay, and then you have to solve it using a data mining task. Yeah, and you have to submit your report together along with your data and code. So first, you have to select the data set. So until you have your data set, you can't do any mining. That is for sure. So data is required. So you can select the data sets from existing repositories. I have listed 2 repositories here. UCI, a machine learning repository, and another one is from SPMF site, authored by Philippe Fournier. So you can go to these sites. You'll be having multiple data sets. And one more option is you can generate the data set on your own. So we call it as a synthetic data set. So you can create your data set based on your problem requirements. So this is the first step. And next, you need to pre-process the data. Pre-processing is required. So, and next one is we need to implement the data mining algorithm for the problem statement. And finally, you need to generate the report. And you have to use this template. I have given you the template. You please go through this link. It's an IEEE format. You follow that. You follow this format and then prepare in that form. You don't use your own formats. Okay, you try to write or complete the report using this format. Yeah. It's just how to select the problem. So one is you can use the existing algorithms. We have the existing algorithms of data mining, such as association or frequent pattern mining, which are called APRAI, FP growth, and the classification algorithms are there, clustering algorithms are there. I've mentioned few for example, that's it. You can select any data mining algorithm. Any data mining algorithm can be applied for your problem. Okay, so you are applying the existing algorithms. Applying the existing algorithms on your selected data set. And the second approach is you can implement your own algorithm, which is better than the existing algorithms. You can create your own algorithm, your own proposed methodology, and then you can implement your problem. So that is the second case. Yeah, for coding this mining, you can use Java or C++, whatever you have learned. Otherwise, we have Python also. Using Python also, you can code it. It's your wish. And coming to the review dates, first review will be on March 23rd and 24th. Yours is batch 2. So March 23rd and 24th. So exactly you have 1 more month. And by this, first review, you need to complete till this abstract, introduction, literature, problem survey, that is literature, data set description, and pre-processing. So 4 plus 4, 8, 8 plus 4, 12, 12 plus 8, 20 marks. So these 20 marks of your first review will be considered for your CLA 1. And the second review is on April 27th and 28th for your batch. So at that time, you need to complete your course project with the code, graphs, conclusion. So this is your second review. Total 40 marks. So they will be converted to 20 marks. Okay. Yeah, and the batch size don't exceed 5. Maximum size is 5. Actually, previously I allowed only 4, but based on few requests, I have maximized to 5. Any doubts in this? I hope every one of you entered your project details in the shared sheet. If not, you complete it quickly and then start work. Any doubts, students? Yes, the next topic is OLAP, OLAP operations, online analytical processing. So this is processing of multidimensional data. So OLAP operations are performed on the multidimensional data. So it allows the managers and analysts to get insight of the information through fast, consistent, and interactive access to the information. So we use these OLAP operations: roll up, drill down, slice, dice, pivot. So we have OLAP servers for implementing these operations. So all these operations are performed on multidimensional data models such as cubes that we already learned. The first one is roll-up operation. We have a cube. So this is the cube with 3 dimensions here: item, time, and location. So this roll-up operation is an aggregation operation. It's an aggregation. You're moving the data from more detailed to less detailed, more detailed data to less detailed data. Okay, you're summarizing means you're performing this aggregation operation. For example, if you consider the location, so in this data cube, you are maintaining the sales information related to each city. If you have 4 cities in total, you are maintaining the sales of Chicago, sales of New York, Toronto, Vancouver. These 2 belong to USA and these 2 belong to Canada. These 2, Toronto, Vancouver belongs to Canada, Chicago, New York belong to USA. So now, if I want to summarize this sales information by maintaining the information related to country instead of cities, I want to maintain in countries. I mean, sales information summarized to countries. So these can be performed using roll-up. You're performing roll-up on the location. So you're rolling up from cities to countries. Okay, actually we have concept hierarchy for this dimension location. Okay, in case of location, we have the concept hierarchy as street, city, province. The province means state, country. Street, city, state, and country. So this is the hierarchy. So now we are moving the data from more detailed to less detailed. You are summarizing. So on rolling up, the data is aggregated by ascending the location hierarchy from level of city to level of country. So you are grouping the data from cities to countries. Okay. So the resultant will be only this. Previously we have 4 rows. Here, if you consider, we are having each record, each row for every city. Now we'll be having country wise. As these 4 cities belongs to these 2 countries, these 2 rows will be the resultant. So you are rolling up on the location from cities to countries. The other dimensions remains the same. Only the change is in the sales information will be summarized based on the country. And next one is a drill down. So drill down is the reverse operation of roll up. Reverse operation means we are moving down the concept hierarchy. We are moving down the concept hierarchy. Here there is an example for drill down operation on time dimension. So this is the initial cube where we are maintaining the information related to quarters. Now we are moving down to months. So this is the concept hierarchy. So day, next level month, monthly sales, next level quarterly sales, next level yearly sales. Now this data cube is maintaining information in quarterly sales data. Now we are moving down the concept hierarchy. You are drilling down from quarter to month. So now this is the result. So instead of quarter 1, we'll be having monthly sales. This is quarter 2, and this is quarter 3. This is quarter 4. Okay. So on drilling down, the time dimension is descended from the level of quarter to the level of month. So it navigates the data from less detailed to highly detailed data, less to more detailed data. So this is more detailed data, this is less detailed data, which is the reverse of roll-up operation. And the next one is slice operation. So this slice operation is the selection operation. It selects one particular dimension from a given cube and provides a new subcube. If this is the input cube, that is the original data cube on which we are performing the slice operation. So we are slicing using the dimension time. The time is equal to Q1. So now we will be getting only this one part of this cube. So which we call it as a slice here. One slice will be retrieved for time is equal to Q1. Okay. So this is a new data obtained, new data obtained. From this 3D data, here you are obtaining the 2D data. The slice will be the 2D. Okay. So for all the items at all the locations, you are retrieving the data for time is equal to Q1. So this is a new data cube formed from this original data cube. So slice operation will select one particular dimension from a given cube and provides the new subcube. And next one is dice operation. So this dice will select 2 or more dimensions from a given cube and provides a new subcube. Slice will select only one dimension, whereas dice will perform on 2 or more dimensions. Yeah, so if this is the cube, and now you're performing dice operation on 2 dimensions. One is location and another one is time. You're performing dice on 2 dimensions. For location is equal to Toronto or Vancouver, and time is equal to Q1 or Q2. And sorry, third one also there, right? Yeah, performing on 3, 2 or more, right? Here we are performing on 3 dimensions. Time is equal to home entertainment or computer. So this is the selection criteria of the subcube. And this will be the result. You are selecting for quarter 1, quarter 2 for the items home entertainment and computer. for the cities Toronto and Vancouver. So this is the new subcube by selecting 2 or more dimensions. So this is dice operation. And next one is pivot operation. So this is a rotation operation. It's a rotation operation. It will rotate the data axis in view in order to provide an alternative presentation of the data. It's a visualization operation which visualizes the data in another form. So actually you're having, for example, if you're having location and item wise data, if you perform a rotation, so the data will be visualized in the form of item and locations. The axis is changed here. This is pivot operation, which is a visualization operation which performs the rotation. So there is an example. So there is an example for a star schema. We have one sales fact table, you can see here, and 3 dimension tables. So in fact table, we have key to dimensions and measure. Here the measure, that is revenue. We have used the measure such as revenue. It's amount measure, one numerical measure. If single fact table with multiple dimensions. Yeah. And if you consider this, you can see here what are all the possible cuboids generated. So what are the 3 dimensions that we considered? Product, time, and a location. So 3D cuboid. 3D cuboid will maintain detailed data, right? It will maintain the detailed data related to each product. Wait a second. Related to each product at each location at each time quarter. 3D cuboid. And 2D cuboids. 2D cuboids will maintain data related to any 2 dimensions. Either item, what is this? Item and time. Item and time. So revenue generated for each item at each time over different locations. So how many we can have here? 3. For location, CA, maybe California, New York, some other FL, Florida, something. So 3 locations. So this is one more example. This is not your textbook example. I have taken some other example. So the values are different here. Don't get confused. So this is based on location and time quarter for items. This is for items. 2D cuboids. 3D cuboid will maintain data related to 3 dimensions, and 2D cuboid will maintain the data related to 2 dimensions. 1D cuboid will maintain data related to 1 dimension. 0D cuboid, highest level of summarization, which will represent the revenue generated over all the products at all the time quarters at all the locations. So this is a single value. Yeah, for this example, we have an implementation. You can refer this OLAP operation using R programming language. Using R is a statistical programming language. It's very simple to understand. You can go through this link there. All the OLAP operations on this particular example, whatever the example that I've shown you in the previous slide, for that example, the implementation is given in this link using R programming language. OLAP operations are implemented using this R. And finally, it's architecture, data warehouse architecture. So it will be having 3-tier architecture. The bottom tier is data warehouse server. The data is collected from external sources. So these are the operational databases and external sources from which the data will be extracted, perform some pre-processing, and then form a data warehouse. So this is the data warehouse which maintains the enterprise warehouse, as well as it can even maintain the data marts. Metadata repository will be there. All the monitoring tools and administration tools, everything will be handled at this bottom tier. That is data warehouse server. The next level is middle tier, which is OLAP server. Whatever the operations that we have discussed now, those are implemented on this OLAP server, online analytical processing server. And finally, the top tier is front-end tools, which represents the reports, the query reports, analysis, and even the data mining results. These are the front-end tools. Okay. These are the front-end tools. That is the top tier, and the middle tier is actual processing of data present in data warehouse. And the bottom tier is the data warehouse server itself, which maintains the data, which collects the data from the external sources and maintains it. So this is your first unit actually. And we need to start our second unit. Yeah. So first unit is all about your data mining and what are the different kinds of patterns generated. That is, what are the data mining functionalities? We have learned about the data mining functionalities such as association analysis, data characterization, data discrimination, classification, clustering, and outlier analysis. And later we have discussed about this data warehouse. Basics of data mining and data warehouse are discussed in our first unit. And the next one is the second unit. So we have 15 minutes more time. I'll give you a brief introduction to your second unit. Shall I start second unit, or can I give you some poll on your first unit? I think I've never conducted polls, right? No response. Okay, then I'll start second unit. Class. So someone asking for the syllabus. So when is your midterm? I think at the end of March.
March 28th, ma'am.
March 20th. So yeah, if it starts at March 20th, okay, let me see the academic calendar. March 20 is Sunday. So from 21st, March 21st, right? Yeah, we have class on, okay, that week is your midterm. Okay, yeah, your syllabus is till March 17th. March 17th, we have a class. So till March 17th, whatever the topics we cover, they'll be in your syllabus. Understand? From March 28th. That's from March 28th. Yeah, that's why I conducted this course project review in this March 23rd, 24. Yeah, March 23rd, 24. Our review will be there. So yeah, you consider it as March 17th. Till March 17th, whatever the topics we cover, mostly first unit, second unit, and some part of third unit. Maybe that's it. Okay. Any other questions related to your midterm? midterm 2, right? That one is midterm 2. Midterm 1 is based on your daily assessments. Is it clear? Till March 17th, whatever the topics will be covered, they'll be included in your midterm. And coming to your end examination, so most of the syllabus will be from the remaining concepts and few from these first 2.5 unit. That you already know. The course project is for CLA 1 and CLA 2. I've already mentioned. Course project is for CLA 1 and CLA 2, 40 marks. 40 marks only, right? CLA 1 20 marks, CLA 2 20 marks. Total 40 marks for your course project. And for midterm 1, I'll consider your daily assessment marks, and also I'll give you one assignment maybe in the next week. I'll give you one assignment related to your first and second units. Small assignment only. I'll give you one small assignment. So based on that assignment and your daily assessment marks, I'll be awarding with 1 marks. Is it clear? Any other questions? What do you mean by course review? Viva only, right? Then again, you're asking for Viva is there or not? The course project, I'll be conducting review. Review means Viva. I'll be asking questions. No? Understood? Okay. Any other questions? Okay. Okay, let me give introduction to your second unit. Yeah. You have 2 parts. One is data pre-processing and another one is frequent pattern mining. One of the data mining functionality that comes under your second part of your second unit. The first part is the data pre-processing. So in data pre-processing, we'll study what are the different reasons of pre-processing, why we need to pre-process the data. This thing we will learn. Question. For Viva, will you consider the whole team performance? Yeah, I'll be conducting Viva batch wise, but marks will be awarded individually based on your performance during Viva. Hope it's clear, Naveen?
Yes, ma'am.
Yeah. Based on your individual performance during Viva only, will be awarded the marks. Okay, so the reasons for pre-processing the data, and next, different forms of data pre-processing. So we have different forms: cleaning, integration, data reduction, transformation. So all these we will learn. And how to perform each step. I mean, how to perform each pre-processing technique. So data cleaning, how can we perform this cleaning? So mainly cleaning consists of handling the missing data and and how to correct the inconsistencies. So this will be discussed here, how to handle the missing values. We have different techniques for handling the missing values, and how to handle the noisy data, errors that occur in the data. So that is one more important part in your data cleaning. We have different techniques for handling the noises, such as binning technique. So this is one technique. And one more is the regression technique. regression technique is also used for handling the noise. We know regression is used for prediction, but it's also used for handling the noisy data. So that we'll discuss here. And then, yeah, I'll discuss with an example. And then outlier analysis. So handling noisy data also involves this outlier analysis, finding out the outlier data. Okay. And data cleaning as a process. As a process, what are the steps involved in data cleaning? We have two steps involved in data cleaning as a process. One is detecting that deviations, that is called a discrepancy detection. First, we need to detect the deviation. Later, we need to perform some transformations on that data transformation. So these are the two steps involved. So we'll discuss that. And next, second form of data pre-processing is integration. So when we integrate the data, what are the issues that should be considered? So they are said to be the challenges in data integration. We'll discuss about these challenges. We have 4 challenges: schema integration, object matching, redundancy handling, using correlation analysis concept, handling this tuple duplication, and data value conflict and resolution. So all these are the different challenges in data integration. So the main thing is redundancy handling, how to find the redundant attributes. We use a correlation analysis technique. It varies for numerical data and nominal data. So we'll learn both the techniques: correlation analysis for numerical data and correlation analysis for nominal data. So these two we will learn here. Okay. And next, data reduction. In data reduction, we have dimensionality reduction and numerosity reduction. Even data compression we have. So reducing the data, reducing huge amount of data to smaller data sets. That is data reduction. So dimensionality reduction means, yes, dimensions will be reduced, means the number of attributes, data attributes involved can be reduced. Numerosity reduction means instead of representing the data in the original form, we can represent it in some other smaller form. That is numerosity reduction. And also data compression. We can perform this compression based on the number of bits used to store the data. So that is data compression. We learn all these data reduction techniques in this concept. Okay, all these are data reduction techniques. Yeah, all these are data reduction techniques. And finally, we will discuss about the data transformation, which is one of the data pre-processing technique. Okay, in data transformation also we have different types. Okay, mainly we will discuss about the normalization technique. We have 3 normalization techniques: min-max, z-score normalization, decimal scaling. So these 3 we'll discuss along with the examples. And finally, we'll discuss about the discretization concept. Okay, so this is one of the data transformation technique. We will transform the continuous values into discrete form. That is the discretization concept. So by this, your pre-processing will be completed. Okay, so all these we need to discuss. Actually, we lost 2 90 minutes classes. That's why we are lagging behind. It's okay, we can complete. So data pre-processing is the preliminary step in the data mining process. In case of data mining process, we learned different steps. The first one is data pre-processing. After data pre-processing only, mining will be performed. So data pre-processing is the preliminary step in the total process of data mining. So it will transform the data into a format which will be more easy and then effective for processing, easily and effectively processed. Okay, so that is yeah. So the main reason for pre-processing the data is in order to improve the quality of the input data. We can improve the quality of the input data by performing this data pre-processing, because the real world data will be incomplete and inconsistent. So by removing these incompleteness and inconsistency, we can improve the quality of the input data if you improve the input quality, it will automatically improve the quality of the output, means quality of the mining results. So this is the main reason for pre-processing. Improving the quality of the data will leads to improving the quality of the mining results. So here I have listed few reasons why we need to pre-process the data. So there will be missing values. Yeah, we need to fill it. And noisy data will be there. We need to smoothen it. We need to handle that noisy data. Outliers will be there. Outlier means the data which is different or which deviates from the existing data points. That is outlier. How to handle these outliers. And resolving the inconsistencies and data redundancy. How to handle this data redundancy. We need to avoid this data redundancy. For all these reasons, we need to pre-process the data. We need to reduce the data to be analyzed. Instead of considering all the attributes present in the data set, we'll select few attributes which are required for the analysis. We are reducing the data for making the analysis easier. And next, we need to improve the quality of the data and thereby improving the quality of the mining results. So these are the several reasons why we need to pre-process the data. Okay, so final aim is to improve the quality of the mining results. This can be achieved only if the input data quality is good. So we pre-process the data. Okay. These are the four different forms of data pre-processing. You can see here. So I've collected this image from your textbook only. So data cleaning, the impurities, these bubbles represents the impurities. Just logically, they are representing these impurities like this. So it's cleaned, so it's shining, right? So this shows the shining of the data. So it's just a logical representation. The impurities in the data are cleaned. And next, integration. You're integrating the data from multiple stores to a single data store. And data reduction. So yeah, here you can see this data input data is having 2000 rows with 126 attributes. You're reducing it to 115 attributes and 1456. Sorry, number of rows is not given here. You're reducing the rows here. You can see symbolically it's represented. This is a large data. This is reduced to smaller data. Okay, so this is data reduction and the transformation. You're transforming the data into a suitable form for analysis. Okay, so all these are different forms of data pre-processing. And in the next class, that is in the tomorrow's class, we'll discuss about data cleaning. Okay. Yeah. Okay, students, do you have any queries? Have no doubts, you can leave. Thank you, everyone.